Hi guys. Okay, let's talk about calorimetry. Calorimetry is a technique in which the amount of heat that is liberated or the amount of heat that is absorbed by an object or a chemical reaction is measured. The device that is used to measure this amount of heat is called the calorimeter. Calorimeters are perfectly insulated containers. But for our laboratories in colleges, we just use these coffee cup calorimeters. In other words, the styrofoam cups as calorimeters. They are called the constant pressure calorimeters because the lid is not too tight. So they are subjected to the outside pressure. These type of containers, which have a tight lid on the top, are more insulated, and these type of containers are called the constant volume calorimeter. So if we were to do a reaction and a gas is liberated, the gas has no way to escape anywhere and it gets trapped inside. So this type of containers are constant volume calorimeters. Okay. Now we know from our experience that the containers or the objects which are in the surrounding also are going to absorb heat. So as we have seen that if I were to take coffee and I mix the sugar with a spoon, after some time I find that one end of my spoon is also going to catch some heat because the heat flows from a hotter side to a colder side. Okay. Now, based on this common knowledge, we can design our experiments in which we can determine not just the specific heat of the objects, but also the identity of the objects. So what do these experiments look like and what are those calculations? Let's find out. All right, so here on the screen you see two types of containers. One of them is having an exothermic reaction. The other one is having the endothermic reaction. So in the exothermic reaction, we see that the object that is placed inside the sealed or the closed, perfectly insulated calorimeter, the object is releasing the heat is trapped inside, and the only way we know how much of the heat is released is through the formula and by noting the increase in the temperature of the surroundings. In the case of an endothermic reaction or a process in which the object is absorbing the heat from the surrounding. So in this case, we are going to see that the temperature of the surrounding goes down because the surrounding has given away its heat to the object. So this is one scenario. Now let us say we want to determine the identity of a metal and we want to determine the specific heat capacity of that metal. Okay, so what do we do? In this case, this is how we are going to set up the experiments. You are going to first take the weight of the unknown metal. Generally, these are pellets. Take the weight of that, put it inside the test tube, put the test tube in a beaker. The beaker has water in it. Boil the water. Slowly, the metal is going to absorb the heat from the boiling water and is going to gain some temperature, or some is going to have some heat into it. Next is you're going to transfer this particular metal, which has become hot, unknown metal pellets, into a coffee cup calorimeter. It's a styrofoam cup which contains a certain amount of water that has been measured. The water is at a lower temperature. The hot metal pellets are obviously at a higher temperature. So when they are mixed, the heat flows from the metal to the water. What happens is that the metal initially was hot. It's going to lose heat to the water. So it's releasing heat. Water, which was at a colder temperature, is absorbing heat. So what we notice now is that the heat is flowing from the hot metal pellets to the cool water. This process continues till the temperature equalizes in both the substances, the water and the metal. So that's going to be a final reading. Okay, so now we see two types of scenarios. One is the heat that is released by the metal, it will have a negative sign, and the heat that is absorbed by the water will have a positive sign. The formula that we are going to use is Q is equal to mc delta T. So what is the meaning of mc? M stands for the mass, C stands for the specific heat, and delta T is the change in temperature. So the amount of heat, let us say M, let's say this is the mass of water times the specific heat of water times the change in temperature. And the change in temperature is the final temperature minus the initial temperature on the water side. And where is this water? This is the water that is inside the calorimeter, okay, is equal to minus the mass of the metal times the specific heat of the metal. And in this case, we're trying to find, that is our unknown, we're trying to find that, and the change in temperature that occurred on the metal side. So the mass is going to be in grams. The specific heat of water is known, which is 4.184 joules per gram degree Celsius. Generally, we use this unit, and sometimes if it's needed, we can also convert it and we can use 1 calories per gram degree Celsius. And the unknown metal specific heat is what we are trying to find. TW and TM. So TW and TM are actually, this is the initial, TW is the initial temperature, and Tm is the initial temperature of the metal. As I mentioned, that the temperature of the water, the initial number is going to be a lower number, and the temperature of the metal is going to be a higher number. So in other words, if we, let's just elaborate this piece right here, where we have delta T. So T final minus TW, which is the initial temperature of water. And here we have T final minus the Tm, which is the initial temperature of the metal. So as you can see that the delta T values are, in this case, in the delta T values, the T final, the final temperature will have the same number. The TW, which is the initial temperature of water, is going to be one number, and then the initial temperature of the metal is going to be another number. So really we are looking at the 3 temperature readings in this. So let us look at this example. We are given this data where we know the specific heat of water, as I mentioned, 4.184 joules per gram degree Celsius, and we are trying to find the specific heat of metal. The mass of the water is 60.0 grams. Now keep this thing in mind, that the density of water is equal to 1 grams per milliliter. So just in case your experiment asks you to measure 60 milliliters of water, then that is going to equate to 60.0 grams of water in mass. Okay, so this is what we have here. Okay, next, on the weighing machine, you can take the weight of the metal pellets, which in this case is 59.7. The initial temperature of water that is in the styrofoam cup, 22 degrees Celsius. And the initial temperature of metal in the hot beaker was 100 degrees Celsius. Now that is the boiling temperature of water. So normally it reaches that, but it could also be sometimes, say 99, it could be 101. So whatever the reading is over here on this thermometer, that reading you are going to take. So the temperature reading for the metal is coming from the water that is in the beaker, and the temperature reading of the water is coming from the water that is present in the calorimeter. Okay, so that's your initial readings. Now comes the final reading. After you mix the metal in the water, that's your final reading. So in this case, that is why you see it is the same, 28.5, 28.5. Now comes a very important piece. T final minus the T initial. So as you can see that the final temperature of the metal is 28.5 and the initial was 100. So it's a negative delta T value, which is negative 71.5. Okay, because the metal has lost the heat. So yeah, there is reduction in the temperature reading. On the other hand, water started off with 22, started off at 22 reading on the thermometer, and it went to 28. So that is why it's a positive number, the change, although you're subtracting 28.5 and 22.0, but you get 66.5 is the positive reading because it's a gain in the heat. So this thing now. Now let's try to solve this problem. Now here's the thing. I have looked into these problems in the way they are explained in the book, and it can be confusing. How come? Because it's confusing in the sense, especially with those negative signs, you know, it can create a mess. So we are going to avoid that, and let's write down our formula first, which is going to be, so a few things here. Negative Q of the metal is equal to positive Q of water. So in other words, this side, the metal is releasing the heat, and the non-metal, I mean the water, is absorbing the heat. So always pay attention to that releasing is going to be negative and leave it that way. The way it is explained in your book, on one hand, on one page, they're saying that it's negative for something that is releasing the heat, that Q should be negative, but when they're doing the calculations, they made it positive. No, there's a better or more right way to do these problems. So let's just look at that one first. Okay, so here is your releasing. So what you're going to do here first, so there are certain steps. Step number one here is find the Q of water, because you know the mass of water, you know the specific heat of water, and you know the temperature change of water. Okay, so let's do that first. So that's for the water. So mass of water given is, here you're given the mass of water is 60.0 grams. Okay, so the mass of water 60.0 grams, 60.0 grams multiplied by the specific heat of water, which is 4.184 joules per gram degree Celsius, times, now here's the thing, we already calculated that, it's 6.5, so times 6.5 degree Celsius. So this is the change in temperature. So now cancel out the, sorry, let's just take a blue color, cancel out the grams and grams, degree Celsius and degree Celsius, and all you are left with is the units for joules. So when you multiply this whole thing, 60 times 4.184 times 6.5, you get this number 1631.76 joules. And this is a positive number, and it makes sense. Why? Because water is absorbing heat. So this is the Q of water. Okay, first do that. Now go back to the second, to the step now. Second step is that we know that the Q of metal, because the metal released that heat, is equal to positive Q for water. So in other words, the Q of water now is, this means that the Q for the metal is going to be, or let's just write down here, Q of the metal is equal to negative 1631.76 joules. Okay, so now we have the So because the metal is releasing the heat, so Q of water is the, so yeah, so this is absorbing. Let's just put this number here. So this is absorbing heat. That is why, you know, you have this, and this is our reference point. And this one is releasing heat. That is why the number is negative. Okay, next is, now we're going to go to the third step. So now at least we know Q of metal is equal to mass of metal times C of metal times delta T of metal, okay, times delta T of metal. Okay, so this is the entity that we need to find, the specific heat of the metal. Okay, so when we rearrange, so now we have this number, which is going to be Q of metal over the mass of metal times the change in temperature of metal. And that is going to be the specific heat of the metal. Okay, so let's put these numbers now. Negative 1361, oh, no, sorry, 1631, sorry, negative 1631 0.76 joules over 59.7 grams, okay, multiply by the change in temperature here was this number, negative 71.5. So multiply by negative 71.5 degree Celsius. Okay, so this whole thing now allows you to cancel out the negative signs. So this technique is better than writing the whole thing in one line and then just doing it, because then it gets very confusing with all these negative signs. So then it creates problems. So anyways, this whole thing, so now you have 1631.76 divided by 59.7 times negative 71.5, and this comes out to be 0.38 joules per grams degree Celsius, 0.38 joules per grams degree Celsius. Okay. Now, generally, you will be given in the labs, because, you know, this is for the experiments in the lab, you will be given either some of the values of the unknown compounds. So it's going to be relating to what is already known to you. So here we find that this is, so from the tables, we find that for copper, this value of the specific heat that we got is the closest. Okay, so this is how you determine the unknown compound also. So our unknown compound is copper. I mean, not the copper. I'm sorry, not the copper. Unknown metal is. I think it's it's getting late. Anyways, so the unknown metal is copper. Okay, and we tally the results from the table. So this is how you calculate the specific heat of metal. And like I said, that instead of doing it this way, instead of doing it this way and plugging in all the numbers right here, because then once you hit the negative charge, then it kind of messes up sometimes, because that's the way it is. Math works that way. But I think if it's easier, would be to first find the metal, first find of the water, and then substitute for the metal, and then go from there, the way I showed you. Okay, so I hope that was easy. And if you have any questions, you know, you can always ask me. But thank you for watching. Bye.